let's get started with the top 5 pieces of information you need to know when it comes to acids and bases. Number 1, just going to scroll down. We're going to go through all of these, is this. There are three reference tables when it comes to acids and bases. Let's take a look at those 3. Here they are. If I go ahead and I reduce them any further, you're basically never going to be able to see them. So the first one here, reference table K, gives you the names and formulas for common acids. Of course, the name of an acid has the word acid in it. Then if I look at the formulas, there is a commonality here in that hydrogen, right, is the only positive ion, or is the donated based on the other theory for acids. So it's easily identified, even if it's not one on this list. Then if I go ahead and I scroll to the second table, known as common bases, you see that the first 3 are a metal with the polyatomic ion hydroxide. So any metal in hydroxide is a base, and then there's a special one here for ammonia. Ammonia is NH3. We don't see OH. So that's where the other acid-base theory is going to come into play. And then finally, anything with acid-base indicators, make sure you have reference table M open. So this could be used for any range of pHs. You're going to go ahead and you're going to use this table, and based on the pH of a solution, be able to determine the color. Now, notice in the middle column here, it says approximate pH range for color change. So if I take a look at methyl orange, below 3.1, it's going to be a red color. Greater than 4.4, it's going to be yellow. And between 3.1, or starting with 3.1 to 4.4, we're going to get a transition of color from red to yellow. And of course, we know red and yellow make orange. So it's going to go from red to orange to yellow. So don't guess. They're here. You just need to know where to look. So let's go back now to number 1. And don't forget that all of our acids and bases, along with salts, are electrolytes. They are all solutions that will conduct an electric current. All right, let's move on now to the second thing to remember about acids and bases. You need to know the 2 ways that an acid and a base are defined. One way is using Arrhenius's theory, where an acid has hydrogen, sometimes also referred to as hydronium ions, in solution, and an Arrhenius base has hydroxide ions. So hydrogen ions are H+, hydronium ions H3O+. These 2 are used interchangeably, and then for a base, OH-. The other acid-base theory defines an acid as donating H+ and a base accepting H+. So it's crucial that you realize that with this other acid-base theory, the hydroxide ions end up as a result of this donating and accepting, but not first you're going to see necessarily right away in the formula. Now, all of the acids listed on the reference table can be defined and identified as both Arrhenius's theory acids along with this other acid-base theory, which is actually called Bronsted-Lowry theory. However, as far as the bases, they can be defined as both for Arrhenius and Bronsted-Lowry for the first three, but not for ammonia. So when I look at the formula for ammonia, it's NH3. See, based on Arrhenius's theory, the OH is not there. However, if I take ammonia and I have it in water, I'm going to form the ammonium ion and hydroxide. So that's where the OH minus comes in. Ammonia is accepting of this H plus, which is also referred to as a proton from water, and forms the ammonium ion and hydroxide. Let's move on to number 3, pH. pH is used to let us know what is going on as far as the solution, whether we might have an acidic, basic, or neutral solution. And you need to know what is happening to the concentration of our hydrogen or hydronium ions in solution when pH changes. A pH question shows up pretty much on every single exam. So let's take a look. If we use a number line, that might help. At a pH of 7, we say that we have a neutral solution. Our hydrogen ion concentration is equal to hydroxide. Okay, our pH of 7 means our hydrogen ion concentration would be 1 times 10 to the minus 7. If the pH drops to 6, we know that means that we have now a solution that's acidic, and our hydrogen ion concentration increases by a factor of 10. Well, 10 times 10 to the minus 7 means with a pH of 6, my hydrogen ion concentration now is 10 to the minus 6. So every time that the pH drops by a factor of 1, I can multiply my hydrogen ion concentration by 10. So let's say it goes from 7 down to 5. Well, 10 times 10 means that it changed or increased by a factor of 100. Let's say we start with a pH of 5, and now we're going down to a pH of 2. Well, in this case, we went from 5 to 4, 4 to 3, and 3 to 2. With the pH dropping each time, the concentration of hydrogen ions increases again by a factor of 10. So 10 times 10 times 10, which in this case then it would have increased by a factor of 1,000. The opposite direction means the opposite is going to happen. Instead of increasing by a factor of 10, we're going to have a drop in concentration by a factor of 10. A pH of 4 to a pH of 8 means that the hydrogen ion concentration, also known as hydronium ion concentration, is going to decrease by a factor of 10. With every unit, the pH increases. So if I'm going from 4 to 5 to 6 to 7 and to 8, it means my hydrogen ion concentration is going to be divided by 10, divide by 10, divide by 10, and one more time, divide by 10. In other words, I would be dividing by 1,000. Okay, it's 1,000-fold decrease. So pH directly relates to the concentration of hydrogen ions. One other way we can look at this would be the following. When I have a whole pH number, just like the pH of 1, that would then be equal to a hydrogen ion concentration of 10 to the minus 1, which is 0.1. For pH of 2, my hydrogen ion concentration is 10 to the minus 2, which is 0.01. So notice here, going from 1 to 2, that the hydrogen ion concentration we would have divided by 10. So let's follow that. If we have a solution now that is becoming less acidic and is going to a pH of 3, my hydrogen ion concentration now would be 10 to the minus 3, which is equal to 0.001. So it can get a little confusing dealing with pH and hydrogen ion concentration, and that's why I think typically for most students, a number line is the way to go. But practice some questions and see what works best for yourself. Please know, again, that pH shows up pretty much on every exam. So let's move on to number 4. For number 4, we're looking at the fact that an acid and a base are going to react with each other. Products are salt and water. This is what's called a neutralization reaction. So neutralization means an acid neutralizes a base and a base neutralizes an acid. This is also a double replacement reaction. Two compounds on the left, two compounds on the right. Now, I've seen Regents questions where they give you the formulas for the acid and the base going to the salt and the water, and you have to pick out which of the choices is a neutralization reaction. Okay, one other thing, don't forget, precipitate reactions are also neutralization reactions. Let's move on to number 5. Okay, so now we have number 5. Titration is a lab process, and it's used to determine concentration. You use one solution versus the other. So it's perfect for acid-base chemistry. The reference table T, has the one equation you need to know for acids and bases. So let's go take a look. So here it is, reference table T. Don't forget, it's the molarity of the acid, volume of the acid. That's going to be equal to the molarity of the base, volume of the base. This is when you have equal moles, right? Moles of H plus are equal to moles of OH minus. With a titration lab process, there's an indicator, typically phenolphthalein, that will change color when this occurs. All right, let's go back. So here's my equation. I would recommend, and what I tell my students, whatever the formula is for the acid that you're given, to put that above the acid side, and whatever formula you're given for the base, put above the base side. Now, the acids and bases so far in the Regents have been kind of a one-for-one situation, meaning something like hydrochloric acid versus sodium hydroxide. So you're getting 1 H for every molecule and 1 OH here for every formula unit. But you could get a situation where you have a diprotic or a triprotic acid or a base that has more than 1 hydroxide. So I think it's important to put the formulas with the equation just in case the Regents question is going to throw you a curveball. So let's just do a couple of questions here from a Regents to finish up this particular video. Okay, here's a couple of questions. You're told that you have an acid, HCl. Here it is, right, and it's up here too. Here's some concentrations of different solutions and pH values. The first one actually is nothing to do with acids and bases. It's asking about sig figs. Oh, sig figs all of a sudden is showing up again. right? So we're looking at solution Z. Here is the concentration. So when you're dealing with significant figures of numbers less than 1, we're going to move from left to right. You have to find the first non-zero, which is the number 1 here, and anything else to the right is considered significant. So it's only the 1 and the 0 to the right. So the answer here is 2. Check out another video to review significant figures. All right, let's check the other two. So 81 is a question asking about the pH of 4. Determine the concentration. So, well, there's two different ways. The first would be just to follow the trend here in the table. So if you look, with every pH value going up, the concentration of hydrochloric acid, you're going to divide by 10. So the next one in line, which would be 4, it's just 0.00010. That's your answer. The other way that you can determine pH and not have to use the pH equation is that a pH of 4, the hydrogen ion concentration then is 1 times 10 to the minus 4. So this and this correspond. Now, the actual equation of pH is equal to minus log of the hydrogen ion concentration. And that's why these factors of 10 are coming in, because of the log. But either way, you're not even pressing anything into the calculator, and you're going to get the right answer. All right, the last one, 82. This is our titration equation, right? It's the math with neutralization. So what we want to do, as soon as you see that or realize, hey, wait a minute, I got numbers in neutralization, or they tell me it's titration, write the equation down from reference table T. So here's my molarity of my acid, my volume of my acid, the molarity of my base, the volume of my base. Now it's just going to plug everything in. Remember I said, though, I got HCl as my acid and NaOH as my base. So it's what volume of 0.25 molar, so 0.25 molar, right, would exactly neutralize. So this is my X. Other side, I got 75 mils, and solution X, the molarity is 0.1. So it's 0.1 times 75 is equal to 0.25 times X. Go ahead and throw it in your calculator, and you're going to get the answer. So you go ahead and plug it in, and you get an answer of 30 milliliters. All right. Well, that ends the top 5 for acids and bases. I would listen again, then start doing some questions that relate to this unit and practice. And if there's something you're forgetting or you're making a mistake, correct your mistake as you go. Hit the like button, that would be greatly appreciated, and keep working hard, and good luck.